Right around the beginning of the 1800s, Avogadro, you may remember him from Avogadro's number, realized that if you take the number of moles of gas that you've got present and you multiply it by some constant, you're going to get a volume. And based on that, we can actually predict a lot of neat things. Take a moment and just fill this one out. Think through how many moles of gas you've got in each of these two cases, and look at how many moles you're going to have in the final example. Okay, so I've got, 2 moles of gas right there, just like it shows in the stoichiometry, and 1 mole of gas there. So I'm having 3 moles of gas, and I'm going to generate 2 moles of gas. That means that I'm expecting this is actually going to compact. And so if I were to actually cause a little detonation of hydrogen and oxygen inside of some sealed container, I'm actually going to predict that because the number of moles has decreased, the volume should also have to decrease too. Boom! We're going to have an implosion reaction. So we're going to have this implode when we actually detonate this. That's kind of a neat idea, right? Now, one thing I want to point out too, we don't have anything in this law right here that specifies anything at all about the molecule type. There's nothing here saying that hydrogen is bigger than oxygen or smaller than oxygen. It doesn't say anything of the sort. It just asks us, what is the total number of moles of gas? And that'll tell me the volume. If I look at the before and after, I can really pick that up too. Now, this is actually telling us that 1 mole of H2 occupies the exact same volume as any of these above. We don't care about its mass. And I like to refer to this as a little bit, I like to call it the I can't see you rule. When a gas is behaving ideally, those molecules are going to be so far apart that their repulsions and attractions are not actually at play. And they're moving around so fast compared to that the tiny bit of attraction or repulsion they can feel at that distance is negligible versus the speed and momentum that they've got as they're moving. That's what we're really talking about when we talk about an ideal gas. They're so far apart, the molecules act like they can't see each other. That's an important piece to remember from this. Now, even more to the point, since every molecule acts the same way when it's an ideal gas, it means that every molecule should take up the same volume as an ideal gas. And if we plug in a set of standard temperatures and pressures, we call this STP, standard temperature and pressure, that's going to be 0 degrees Celsius at 1 atmosphere. If we plug those into the ideal gas law, we would determine is that all gases should take up 22.4 liters when they're at 0 degrees Celsius and at 1 atmosphere of pressure for 1 mole of gas. So I don't care if you're talking about hydrogen, one of the smallest molecules we've got, or something like sulfur hexafluoride, which is actually a fairly large and fairly heavy molecule. You could even go all the way to talking about uranium hexafluoride. And it should act exactly the same way and take up the same amount of volume as hydrogen gas does. That's a consequence of Avogadro's law.